this video we're going to talk about rotational kinetic energy and the moment of inertia calculations. So let's see what is rotational kinetic energy and why should we have a kinetic energy associated with rotations. So let's say that I have this arbitrarily shaped object, as you can see in the figure, that is being rotated around the z-axis. This is a continuous object, but I can think of this continuous object to be made up of small particles, each with mass m. So for the ith particle that is at a distance r sub I from the origin, that has a tangential velocity v sub I and has mass m sub I. I can basically see that for this particle, because it has a tangential velocity, it must have a kinetic energy associated with its motion. And the whole object is rotating around the z-axis with angular speed omega. Okay, so individual particles with masses m sub I make up the rigid object. So I is basically the particle index, and there is kinetic energy associated with their motion. There is a tangential velocity v sub I, and there is the radial distance r sub I to the rotation axis. Okay, so the kinetic energy k sub I of this ith particle that makes up this object is obviously 1 over 2 its mass times its velocity squared, 1 over 2 mi vi squared. Now this is made up of many such particles, so if I try to calculate total kinetic energy associated with this rotation, I have to sum up the contributions from each such particles. So k sub r, the total kinetic energy, will be the addition of kinetic energies of such particles, and that will be a sum over the particle index I, 1 over 2 m sub I v sub I squared. Now for circular motion, remember that the tangential speed v sub I has to be related to the angular speed. So it's going to be omega times r sub I, right? So that comes from our study of circular motion. So I can write the total kinetic energy of rotation to be sum over I, 1 over 2 m sub I omega squared r sub I squared. Well, omega is the common angular speed for these particles, so I can take this out and also take 1 over 2 out. 1 over 2 sum over I mi ri squared times omega squared. So this quantity that appears in the kinetic energy expression, the sum of masses multiplied by their distances to the rotation axis squared, I'm going to define it as a new quantity. I call this moment of inertia. So I show it with I, sum over I mi ri squared. That's the definition for discrete set of particles, and It's called the moment of inertia. Now, what is the unit of this moment of inertia? You can see I have a mass multiplied by distance squared, so the SI unit would be in kilograms meter squared. So with this definition, I have the rotational kinetic energy written as 1 over 2 moment of inertia omega squared. This is the rotational kinetic energy. Okay. Now, so when we were discussing in the previous video the rotational kinematics, we found that there was some analogy between translational and rotational motion, and I can take this analogy further and I can say that this moment of inertia in translational motion is analogous to mass in rotational motion is analogous to mass in translational motion, and omega of the rotation angular speed is analogous to v, so that 1/2 I omega squared is analogous to 1/2 m v squared. Okay, so there is a similarity in the equations describing these two different types of motion. Now, if it's a continuous object that we're talking about that is really not made up of discrete particles, or if the particle sizes are too small, which is what we should have done in this case, I have to basically extend this discussion for a continuous object that is made up of very small particles. The moment of inertia is going to become the limit as these small masses go to 0 sum over I Ri square delta m I, which is really nothing but an integral r square dm. Okay, so how do I calculate dm? This is something we have discussed before in the center of mass calculations. It depends on how many dimensions we have for this object. So dm is equal to mass density times volume if it's a three-dimensional object, mass density sigma times area if it's a two-dimensional object, or mass density lambda times the length ds if it is a one-dimensional object. So one-dimensional object, for example, a rod, two-dimensional object, a disk, three-dimensional object, a sphere. Okay, so the moment of inertia is in one of these forms: rho r squared dv, or sigma r squared dA, or lambda r squared ds. Okay, so in general we found that it's written in this form, r squared dm. It's the dm that is changing depending on the dimensions of the continuous object of interest. And if you remember, for uniform mass distribution, we have the mass density rho is equal to total mass divided by the volume. Mass density sigma is total mass divided by total area, and mass density lambda is total mass divided by the length of the object. So this is for uniform mass distribution. We have this result. Okay, now we're going to see how we can calculate the moment of inertia of several different mass configurations. We're going to start out with a simple case, a discrete mass distribution. Here I have 3 point masses. This is particle 1, this is particle 2, this is particle 3, and they are at the corners of an equilateral triangle which has a side L here. So I want to know the moment of inertia around for rotations around x, y, and z axis. Okay, so let's start with the x-axis rotations. Okay, so what is the distance between particle 1 and the x-axis? So particle 1 and particle 2 are on the x-axis. So their distance to the x-axis, r1 and r2, are 0. Particle 3 is not on the x-axis, so here I have a distance L over 2. Here I have L. So I have to calculate what is the distance between particle 3 and the x-axis. So that's this distance I have to calculate. And obviously I can use this right triangle with sides hypotenuse L and one side L over 2. So this is my right triangle here. So R3 would be equal to square root of L square minus L square over 4. So that's going to be square root 3 over 4 L squared. That's R3. So the moment of inertia for rotations around x-axis will have 3 contributions. From particle 1 I have 0, from particle 2 I have 0, from particle 3 I have m r3 squared, which is m 3 over 4 L squared, or in other words 3 over 4 ml squared is going to be my answer for this case, because there are no contributions from particle 1 and particle 2. Now for the y-axis calculation, I have particle 3 on the y-axis, so it will have no contribution. R3 is 0. It has 0 distance to the rotation axis. What is the distance for particle 1 and particle 2? They have a symmetric situation here. They are located at minus L over 2 and plus L over 2 here. So this is at minus L over 2. This is at plus L over 2. So the distance is L over 2. The moment of inertia for rotations around y-axis will be m times L squared over 4 for particle 1, m times L squared over 4 for particle 2, and 0 for particle 3. So this will be 1 over 2 ml squared. So that will be the answer for y-axis rotations. And for z-axis rotations, so that's the axis at the center. So what is the distance from the first and second particles to the z-axis? They're also L over 2. And what is the distance from the third particle to the z-axis? That one is what we have calculated here. It was square root 3 over 2 L. So that's the red line. So R3 is square root 3 over 2L, because we calculated it before. It's the same distance to the x-axis and z-axis in this case. So the moment of inertia for rotations about the z-axis will be ml squared over 4 for particle 1, ml squared over 4 for particle 2, and m3l squared over 4 for particle 3. So this is going to give me a total of 5 over 4 ml squared. So this will be my answer to this part. Okay, so I hope this discrete mass distribution is clear. That's the easiest possible moment of inertia calculation you can think of. Now let's move on to a little bit more complicated situation. I have a rigid uniform rod rotated around one end, which is the y-axis in this case. I want to know the moment of inertia. First of all, I have to note that this is a one-dimensional object. So it has a uniform mass distribution lambda, and if the total mass of this rod is m, then m over L will be its mass density. So I call m total mass. Now, for continuous objects, remember that moment of inertia is integral r squared dm. So I have to find small particles that make up this object. So what I'm going to do is I will move to a distance x from the origin, find this particle which has a width dx. Okay, so it's a one-dimensional object. So I ask myself, what is the mass of this particle dm? It has to be lambda dx. And what is its distance to the rotation axis? That is x. So the moment of inertia will be the sum of the contributions from all such infinitesimal particles. So I will have x squared lambda dx, and x will run from 0 to L, so that I will cover all such particles. So I have these particles, many particles that I'm counting. So this will be, since lambda is a constant, it stays here, x cubed over 3 from 0 to L, and so that will be lambda L cubed over 3. Now, what is lambda in this case? Lambda is m over L, so it is m over L, L cubed over 3. So the moment of inertia is 1 over 3 ml squared. Okay, so obviously the total mass should be given in order to get the moment of inertia. It's 1 over 3 ml squared for this case. Okay, now let's have the same rod rotated around its center of mass axis. Okay, so central axis. It's again uniform, and I take a small element here which has mass dm, that is lambda times dx. So this is located at x, and in this case the moment of inertia will be integral r squared dm. Again, r is equal to x in this case, x squared, and dm is lambda dx. So the only thing that changes is the limit of my integration. So I have to go from minus L over 2 to plus L over 2. So I note that total mass is again capital M. So the moment of inertia will be lambda x cubed over 3 between the limits minus L over 2 and plus L over 2. So it will be lambda over 3 L cube over 8 minus plus L cube over 8. So this will be equal to lambda over 3 L cube over 4. Okay, so the moment of inertia will be lambda L cube over 12. Lambda is m over L, so 1 over 12 m L squared will be the answer, because one of the L's will disappear. I substitute for lambda here m over L. How do I know lambda is m over L? Because it's uniformly distributed mass. So you can see, depending on where the axis of rotation is, I'm getting a different answer. For rotations around an axis that goes through one end, it's 1/3 ml squared, and for rotations around the central axis, it is 1 over 12 ml squared. Okay. Now I'm going to have a uniform ring of radius r rotated around its central axis, and again I call the total mass m here. Sorry, I forgot to give this. The same story, so I have to pick a mass element. Okay, so I take a small element here, so this is at a very small angular separation d theta. Okay, and this is, again, since it's a ring, it's one-dimensional. So the mass here is going to be equal to lambda times ds, ds being the arc length. So what is ds? This we have done several times. It's going to be equal to the radius times the angle, r d theta. So that 2 pi r will be the circumference. So for an angle of 2 pi, we have 2 pi r arc length. For an angle d theta, we have r d theta arc length. So my dm is going to be lambda r d theta. Now the moment of inertia is integral r squared dm. The rotation axis is the central axis. So my r is capital R, the radius of the ring. So it will be integral r squared lambda r d theta. And I have to cover all angles. So if this is my x-axis here, I define my angle with respect to the x-axis. It has to go from 0 to 2 pi, so that I cover the whole ring, all such mass elements, contribution from all such mass elements to the moment of inertia. So this is going to be equal to lambda r cube theta from 0 to 2 pi. So it will be 2 pi times lambda r cube. Now the question is, what is lambda here? Lambda is the mass, total mass, divided by the total length. What is the total length? It is 2 pi r. Because it's a uniform mass distribution. And the moment of inertia I calculate is 2 pi r cube times m over 2 pi r. So it will be m r squared. So that will be the answer for this ring rotated around its central axis. Okay, so I want to move on to the disk now. So it's a two-dimensional object, uniform disk of radius r, total mass m, again capital M I call it, that is rotated around its central axis. Again, in this case, I have to pick a mass element, so I'm going to go to a radial distance small r here and make an angular separation d theta, and I pick a mass element. Okay, so you can see that this mass element has two dimensions. One side is r d theta, the other side is dr. Okay, so this has an area r dr d theta. So r d theta is the arc length and dr is the incremental dimension on the radial axis. Therefore, it's going to have a mass dm sigma times dA. So it's going to be sigma r dr d theta. And the other question I have to answer is, what is sigma? If it's a uniform distribution of mass, this is the total mass divided by the total area, pi r squared, where capital R is the radius of the disk. Okay, so the total moment of inertia, I have to calculate the contributions of all such masses, is integral r squared dm. Now I ask myself, what is the distance from this small mass element to the rotation axis? The rotation axis is here, the central axis. It is integral r squared, and for dm I have to substitute sigma r dr d theta. And now I realize that because it's a two-dimensional object, this is actually a double integral. And in order to cover all such elements, small r has to go from 0 to capital R, and the angle has to be spanning the full range of the disk, so it has to go from 0 to 2 pi. So let me write this in a nicer way. Integral from 0 to 2 pi, integral from 0 to r, sigma r cube dr d theta. So this will be equal to, if I perform this integration, sigma r to 4 over 4, that's the r integral. The theta integral is independent, it just gives me an angle theta, so it's 2 pi. Alright, so this is going to be equal to sigma pi r to 4 divided by 2. And now if I substitute for sigma m over pi r squared multiplied with pi r to the 4th power divided by 2, I find that this is going to be now m r squared divided by 2. So this is the answer for the uniform disk. Okay, now I have two identical uniform rods of length L, so they have a total mass m, let's say, total mass for one rod. Okay, and they're identical, so they have the same masses. Now this configuration of the two rods is either rotated around y-axis or z-axis. So let's first on rotations around y-axis. So y-axis rotations. Again, I'm going to pick up a mass element, so let's use different colors for different rods. So I pick up a mass element here that is located at position x. It has width dx. It has dm is equal to lambda dx. And for the other one, I pick up a mass element here. This is at location y on the y-axis, and it has width dy, and it has a mass lambda dy. Okay? Now, what is lambda? Because it's a uniform mass distribution, lambda is the total mass divided by the total length of the rods. It's the same lambda. The moment of inertia is integral r squared dm. So I look at the rod that is on the x-axis from 0 to L. I have what is the distance between the mass element and the y-axis. It is x, so it's going to be x squared, and dm is lambda dx. Okay, and for the second rod I have from minus L over 2 to plus L over 2. The distance between mass elements and the y-axis is always equal to L, so it's going to be L squared lambda dy, right? So that's this distance here. Let me show it. This distance here is always equal to L. Now, this is going to give me lambda x cubed over 3 from 0 to L, and this is going to give me lambda L squared y from minus L over 2 to plus L over 2, and I substitute also for lambda m over L, so this is going to be lambda L cubed over 3. This is going to be lambda L squared times L over 2 minus L over 2. So this will be lambda L cubed over 3 plus lambda L cubed. Okay, so I substitute for lambda m over L, L cubed over 3, and m over L, L cubed, so it's ml squared over 3 plus ml squared. 4 over 3 ml squared is going to be my answer for this case. Okay, now if I do rotations around z-axis, for the horizontal rod there's no difference, right? But for the vertical rod, actually, there will be a difference. So let me work on the z-axis here. Okay, for z-axis rotations, when I pick up this mass element on the vertical rod, I have to calculate what is the distance between this mass element and the z-axis. So what is that distance? Well, that distance here is going to be equal to, because this is a right triangle, it will be equal to square root of L squared plus y squared, because that is located at y. Now if I calculate the moment of inertia again, integral r squared dm. For the horizontal rod there is no change. It is the distance to the z-axis is x, so it's x squared lambda dx. But for the other one I have the integral r squared is L squared plus y squared lambda dy. And once again this goes from minus L over 2 to plus L over 2. This goes from 0 to L. So this is going to give me once again ml squared over 3, because I have done it already here in the previous axis, y-axis. I don't need to worry about that. And for this one I have L squared lambda times y plus y cubed lambda over 3 to be evaluated between minus L over 2 and plus L over 2. So this will give me ml squared over 3 plus lambda is m over L times L squared times L over 2 minus L over 2 will give me just an L. And then here I have plus 1 over 3. Lambda has been taken out as m over L. Y cube, it is L cube over 8 minus L cube over 8. So I will have a factor of 2 here. So you can see that my answer here is ml squared over 3 plus ml squared plus ml squared over 12. If you calculate the total, this is actually 17 over 12 ml squared. Now, the reason I have done this example is because I want you to notice that this ml squared over 12 was the answer we have found in the previous examples, one of the previous examples for rotations around the center of mass. So that was 1 over 12 ml squared. And then this one, you can think of it as the L is the distance between the center of mass of the rod and the rotation axis, that is L. So ml squared plus ml squared over 12. So this is actually showing you a very famous theorem. I'm not going to prove to you. If you're interested, you can read it in the book. This is known as parallel axis theorem, which says the moment of inertia for rotations about an axis that is parallel to an axis that goes through the center of mass, it's the moment of inertia for rotations around the center of mass axis plus total mass times d squared, where d is the distance, between the center of mass and the rotation axis. So this is an important theorem. It's quite useful in some cases, so you have to know it by heart. Once again, I know the moment of inertia with respect to center of mass, that is this one. So let me clarify it here. So I have ml squared, that is md squared. So I have a rotation axis. So imagine that you have an axis of rotation that goes through the center of mass. So these two rotation axes are parallel to each other. This is perpendicular to the page. So I can use parallel axis theorem. So I find the moment of inertia with respect to center of mass, that is ml squared over 12. Ml squared over 12 is the center of mass. Rotations for about an axis going through the center of mass. And now I want to know the moment of inertia for rotations around an axis that is parallel to the center of mass axis, that is the z-axis. I have to find the distance d between the two rotation axes, that is L in this case. So it's ml squared is equal to md squared. So this part of the answer is actually showing you the parallel axis theorem. Okay, I hope this is clear. Now I want to look at two three-dimensional objects in order to complete this discussion. And there are two ways of calculating the moment of inertia for three-dimensional objects here. You can use integral r squared dm, And if you already know the answer for something that makes up this object, it's integral di. This is a hollow sphere. It's a spherical shell, in other words, that is rotated around its central axis and it's uniform. Okay, so as you can see from this figure, this is actually a two-dimensional object because it's a shell. Okay, so what is the mass density for this one? Sigma, that is the total mass, I will call m, total mass m, divided by the total surface area. What is the total surface area of a sphere? It is 4 pi r squared. So it's m divided by 4 pi r squared. Now what I'm going to do is I'm going to take a ring in order to get my infinitesimal mass here. So I'm going to take a ring. All right, so this ring does not have the radius r, it has a different radius. So if this is the angle theta here, I call this angle theta, the radius of the ring, small r, would be equal to r sine theta. r sine theta. Okay. So what is the area of this ring? We have the circumference 2 pi r, 2 pi r sine theta, that is the circumference, multiplied by this dimension here. So what is this dimension? That is the circular arc, right? ds is equal to r d theta. So if you multiply this by r d theta, you will have the area that is covered by a region made up of such rings. So the mass will be sigma dA, that is sigma 2 pi r square sine theta d theta for this ring. So if I substitute for sigma m over 4 pi r squared, 2 pi r squared sine theta d theta, this is going to give me for the mass m over 2 sine theta d theta. Okay, so when d theta is going to 0, this is a ring, and for a ring I know that for rotations around the center of and around the center I have a moment of inertia mr squared. How do I know? I go back to my ring example and this is what I find. mr squared was the moment of inertia. So I'm going to use this result basically for rotations around the y-axis here. What is the distance r, distance from the ring to the center? It will be, in this case, r sine theta. So that has to be replaced by r sine theta. This is coming from the previous example, so don't get confused with the r's here. So I'm going to have a di is equal to dm r square sine square theta. So the total moment of inertia here, I, is integral. The angle has to go from 0 to pi, so that I will cover all such rings, dm integral di, which is dr square sine theta times sine square theta times dm. And so let's calculate what this di is. It is m over 2 sine theta d theta r square sine square theta. So this will be m over 2 r square sine cube theta d theta. Okay, so if I substitute that into this integral, it's the integral from 0 to pi mr squared over 2 sine cube theta d theta. So the question is, what is the integral of sine cube theta? Okay, so let's open up some space here in order to calculate this integral. So what I need is this integral from 0 to pi sine cube theta, which can be written as sine theta times sine square theta, which is 1 minus cosine square theta d theta. So this is mr squared over 2. The integral of sine theta d theta is minus cosine theta, and the integral of cosine square theta minus sine theta d theta, that is like if you call cosine theta is u, minus sine theta d theta is du. So you will notice that this is integral u squared du, and you have u cube over 3 as the answer. So this will be plus cosine cube theta over 3 evaluated between 0 and pi. So this will be mr squared over 2. I will have cosine pi is minus 1, minus minus 1 is plus 1, minus minus plus cosine 0 is 1, so this is going to give me a 2. And then here I will have minus 1 over 3 for cosine cube pi over 3, and another minus 1 over 3 from the limit at 0. So this will give me 2 minus 2 over 3 mr squared over 2 times 4 over 3. The answer is 2 over 3 mr squared. So this is one way of doing it. There is another way of solving these problems, and I'm going to demonstrate that to you for the solid sphere. Now in the notes you will notice that the solid sphere moment of inertia for rotations at about the center is found by forming spherical shells and using the same trick. I is equal to integral di, because you already know the answer for a spherical shell. You add up the contributions from each such spherical shells. Instead, what I'm going to do is I'm going to use the brute force method. I will find a mass element in this sphere, and I will calculate the contribution from each such mass elements, general mass elements, to the moment of inertia. Okay, so what is the mass element, a general mass element I can find here? So I go to a distance, small distance r. This is at an angle theta, and its projection onto the xz plane here is going to be here, making an angle phi with the x-axis. Okay, So you have to go in 3 dimensions in order to get a small mass element here. So following R here, I go a small distance dr, so that will give me 1 dimension. And then following the angle theta here, I go through a small angle. This will give me another dimension, r d theta. And the 3rd dimension will come from the projection of this r to the xz plane, as I have demonstrated here. So that's going to be r sine theta. So you have a radius r sine theta, and then you vary the angle phi by a small distance. So you will get an arc length r sine theta d phi. Okay, so I will have r d theta, that is rotation on the xy plane. Then I will have dr, that is on the radial axis, and then I will make another rotation for the projection of this. So this is going to give me r sine theta d phi. So basically I'm varying this one. So the volume element here is r square sine theta dr d theta d phi. Okay, so what is the mass of this element? So that's what I'm doing here, calculating the mass of this element, dm. dm is rho dv. It is, because it's a uniform solid sphere, m divided by 4/3 pi r cube multiplied by the volume, r square sine theta dr d theta d phi. So the mass of this element is 3m over 4 pi r cubed r square sine theta dr d theta d phi. Okay. And what is the distance between this mass element and the rotation axis? That would be this distance here. What is that distance? That distance is r sine theta. Okay, so for each such mass element. So the moment of inertia will be then integral r squared dm. Well, this r is basically not this r, it is r sine theta. Okay, so this is going to be, therefore, moment of inertia is integral r square sine square theta, the distance between the mass element and the rotation axis squared, times its mass, 3m over 4 pi r cube, r square sine theta dr d theta d phi. Okay, and so the moment of inertia is 3m over 4 pi r cube. I'm going to start performing the integrals now. The phi integral goes from 0 to 2 pi, the theta integral goes from 0 to pi, the r integral goes from 0 to capital R. So I have r to 4 dr sine cube theta d theta and d phi. So these integrals, the phi and the r integrals, are the easiest, so let's perform those two. 3m over 4 pi r cube multiplied with r to 5 over 5, and from phi integral I will get 2 pi, and then I have a remaining integral from 0 to pi sine cube theta d theta. So the moment of inertia is this 2 will get rid of this one, so this will be becoming 10 now. The pi will get rid of the pi, so 3m, so this 3 will make this 2, 3m r squared over 10 multiplied by the integral 0 to pi sine cube theta d theta. And this integral actually I just performed somewhere else. Where did I perform this integral? Let me see. Yes, here, this integral from 0 to pi sine cube theta d theta. And that actually gives me a factor of 4 over 3. So let's not do that again. So it's 4 over 3, 3m r squared over 10 times 4 over 3. So this will give me 4 over 5 m, no, sorry. This 4 will give me a 2, this will give me a 5, so it's going to be 2 over 5 mr squared. So you can verify this answer with the other method. If you go through the shells and calculate this moment of inertia, obviously it's easier. It gives you an answer right away, but then you have to know the story for spherical shells beforehand, which is something we have done before. Okay, so I'm going to leave to you the triangle and rectangle examples in the notes. You can go through these on your own. And next time we will talk about torque.